In this section, we look at Lagrange multipliers as another method of finding the maximum or minimum value of some function given a constraint. Before we begin with anything more formal, consider an informal example. Let's say we were trying to find the maximum volume of some rectangular solid that was inscribed within a sphere. Okay, well, there's lots and lots of rectangular solids that can be inscribed within any given sphere. So let's say here's our sphere. Okay, well, that's one rectangular solid. Now, clearly, that's not the biggest one I could have inside of this sphere. I can go smaller or I can go bigger. Now, if I go a little bit bigger, well, that's certainly closer to what I want, but that's not quite right. If I go too big, however, that's also not correct. Because that's no longer bound by my sphere. What I want to do is I want to have exactly the right size. I want to have exactly, I want to make it just as big as I can while still meeting the conditions. So let's say I'm trying to maximize the volume of a cube. Okay, well then my volume is a function of x and y and z. Okay, so I have a constraint. For example, my sphere. My sphere is not unknown. I have exactly what sphere I'm looking for. So this right here is called my objective function. You may remember this from a Cal 1 class. The thing you're trying to maximize or minimize is called your objective function. Your constraint is the equation, or sometimes equations, that limit how big or how small your objective can get. Now, your constraint is not a function of several variables. It's one specific instance. Well, it's one specific instance. You can think of that as being a function equals to a constant. So here, your constraint could be something like f of x comma y is equal to a very specific, or I guess I could say f of x comma y comma z is equal to a very specific constant. So c for constant, right? Okay, so now my objective function is, well, it's not equal to a constant. Well, no, because we don't know what it is. However, we'd like to find what constant this is. We'd like to find one specific instance of our objective function as well. Our objective function is describing the volume of not one rectangular solid, but an infinite number of rectangular solids, many of which are too small, many of which are too big, and only one of which is exactly right. So here, when I'm looking at my objective function, this is really a family of functions. It's a whole collection of volumes of rectangular solids or pyramids or spheres or whatever it is you're looking for. So this is really a family of solids. Okay, but what I'm looking for is I'm looking for one in particular. Okay, so I want this to be, well, that would be a level curve, wouldn't it? If I have a bunch of things in a family, a bunch of different functions, but I want one in particular, well, that would be v of x comma y comma z equals to, well, whatever the volume of this one is in particular. Oh, so what I'm looking for is I'm looking for a level curve. A specific case of our function, of our objective function. For the next part of this explanation, I'm going to simplify my graph here a lot. Let's say we were just looking for maximizing things on the plane, just because it's going to be very difficult to draw this next part in space. Here is my constraint. It is a single function, a single instance, x squared plus y squared is equal to 25. Okay, so this is my constraint. Now, the thing I'm trying to maximize, the thing I'm trying to find the maximum or minimum value of, the objective, is going to be not just a function, a specific instance, but rather this function equals to a bunch of different constants. Okay, well, that's going to have a whole family of possible results, each of which differ by just a constant. What I want is I want the one that just barely meets the constraint. Because if I don't meet the constraint, well then I'm outside of my sphere. I didn't meet the requirements that I wanted. But if I go beyond just barely meeting the constraint, and I meet the constraint by a lot, well that means here my cube would be the really tiny one that's inside the sphere. I want the one that just barely touches the constraint. I want the one that just barely fits inside the sphere, because that'll be the biggest one that I can put inside. Oh, but if those two just barely touch, that means that they only touch at that one point. So that means that they share the same tangent line. So here, these two curves, the one that I want, the level curve that I'm looking for, the answer to the maximization of my objective function, is going to be the one that has the same tangent line as the constraint at the point where they meet. Oh, but one thing that we remember from previous sections is that whenever you have a tangent line, the tangent line is orthogonal to the gradient vector. Well, here I want this to be orthogonal to this constraint curve, but I would also want it to be orthogonal to this objective curve. So what that means is I want to find where these two functions have, well, here I would say they're the same, but they're not. They might be opposites of each other. Or one might be a lot longer than the other. So they're just traveling in the same direction. So then I want to have my gradients be parallel to each other. We want the constraint function and the objective function to have parallel gradients. This is by no means any kind of proof. This simply motivates our following theorem. But then we can prove that theorem. So here we go, theorem. And this is one of those theorems that has a name attached. This is Lagrange's theorem, named after the French mathematician Joseph Louis Lagrange. For any of my students that speak French, my apologies for totally butchering that name, I'm sure. For anyone who's thinking that name sounds familiar, you may recognize it from physics or astronomy. The Lagrange point has to do with the point between bodies that are orbiting each other. It's a sort of a halfway point of centers of mass. All right? So Lagrange's name is attached to at least a few theorems in physics and astronomy. But for now, the theorem of his that we want states the following. Let f of x comma y and g of x comma y have continuous first partial derivatives. So these are two functions of x and y. They have continuous first partial derivatives such that f has an extrema at some point x naught comma y naught on the smooth constraint curve, constraint, TRA, constraint curve, g of x comma y equals to c. So here's our constraint. It's a function equal to a constant. And then you have another function, which is our objective function. All right, so it turns out that the objective function has a maximum, given that constraint, at the point x naught comma y naught. Okay. If the gradient of g at x naught comma y naught is not identically the zero vector, then there exists some real number which in his theorem he used the symbol lambda. There exists a real number lambda, which here we call that the Lagrange multiplier. Where lambda is called the Lagrange multiplier. Such that the gradient of f at x naught comma y naught is equal to lambda times the gradient of g at x naught comma y naught. Or in other words, the gradient of f is a multiple of the gradient of g. Or in other words, the gradient of f and the gradient of g are parallel to each other, as was suggested from our earlier motivation. But again, motivation does not make a theorem, and it certainly does not make a proof. This simply suggests why we might suspect that such a thing was true. The proof is as follows. All right, so let's go ahead and let g be a function of x and y. Let's let g of x comma y be some constant. So that's our constraint curve. Let's let this be represented by some vector valued function r of t, which is x of ti plus y of t j. So we've gone ahead and parameterized our curve using a vector valued function of t. Let that be represented where, so here we want some specifics about this, where r prime of t is not equal to the zero vector, and x prime of t and y prime of t are continuous on an open interval I. And here all this really means is that the gradient is not zero and that you have a smooth constraint curve, as was required by the conditions of our theorem. Okay? So right now we're really just reiterating the conditions. Now, let's go and define a new function. Let's go and define h of t as f of x of t comma y of t. So here we've reparameterized. We've taken our function f, our objective function. We've parameterized it with respect to t, and we're calling that h of t. Okay? Now, we know that f has a maximum on x naught comma y naught. Well, actually, maybe not a maximum. It has an extremum. Since f has an extrema, at x naught comma y naught, then that means h of t naught, which would be, well, that would be, replace those with t naught. That would be f of x of t naught comma y of t naught, which would equal to, well, that would be t naught, that would be x of t naught would be x naught comma y naught. Okay, so we know f has an extrema here, which means h of t naught must be the extrema of h. Right? If these are all equal to each other, this is an extrema of the function. Well, h is just a parameterization of this. So then that must be an extrema of the function h. All right, well, if that's an extrema, well, then that means that at t naught you have to have a critical number. All right? That's a critical point, which must make that a critical number. Oh, well, if it's a critical number, that means it's either the derivative is undefined or the derivative is equal to 0. Well, we know the derivative is not undefined because we have continuous partials. We have continuous derivatives. Everything's continuous. So we know they exist. So here, h prime of t must exist since f is continuous. Around the point x naught comma y naught, then h of t naught is also I guess I should say it the same way. H is continuous around t naught. Oh, but if it's continuous, oh, actually, I could say something even stronger. I know f has continuous first partial derivatives. Okay, so then that means f is differentiable. So I can say something even stronger. So since f is differentiable, right? Knowing that I have the derivatives and that they are continuous at that point is sufficient to know that they are differentiable. Right? That's one of the theorems that we had about differentiability. It's not enough to know that the two partials exist, but if they exist and are continuous, as we know here, they exist and are continuous, then that means f is differentiable. So then h is also differentiable. In the Cal 1 sense, since it's a function of one variable, it's differentiable around t naught. So, since that's an extrema, then either the derivative is undefined or 0. But we know it's differentiable. It has to have a derivative. Oh, so then that must mean that h prime at t naught, it has to be defined since it's differentiable, so then it must be 0. Because t naught is a critical number of h. So I guess we have to go on to another page here. Well, here. Okay, so let's see, where are we? Critical number of h. All right. But h prime at t naught, well, that's equal to h sub x at x naught comma y naught times x prime at t naught plus f sub y at x naught comma y naught times y prime at t naught. That's the chain rule. Right? If you're taking the derivative of a composition, after all, h is f of x of t comma y of t, then that would be the derivative of f with respect to x times x prime plus the derivative of f with respect to y times y prime. This is just the chain rule. But since that's equal to this, then that means h prime at t naught is equal to, well, that right there, that's the gradient dotted with r prime. After all, r is equal to x of t comma y of t. So if I'm taking the derivative of both of those, well, that's the derivatives of the components of r. So that's going to equal to the gradient of f, that'll give us those components, at x naught comma y naught, dotted with, well, that's the derivative of the components of the vector r, again, at t naught. Okay, but over here, we just saw that h prime of t is equal to 0. And since h prime at t naught is equal to 0, that implies that the gradient of f at x naught comma y naught dotted with r prime of t must equal to 0, which means that r prime of t and the gradient are orthogonal. The gradient of f at x naught comma y naught is orthogonal to r prime at t naught. But since g of x comma y equals c, that's a level curve, and it has x naught comma y naught on it, then we know that the gradient of g of x comma y will be orthogonal to the line that's tangent to g at x naught comma y naught. Okay. So that means that the gradient of g at x naught comma y naught is orthogonal to the line that is tangent, or I guess to the vector that is tangent to the curve at x naught comma y naught. Oh, but that's also r prime of t naught. If you have a level curve crossing through a point, then the gradient is orthogonal to the derivative of the curve, which, of course, the derivative of the curve at that point, that would give us the line tangent. So this is the tangent line at that point. This is the gradient at that point. And as we saw when we first defined the gradient, those two are orthogonal to each other. Okay, so that means that del f is orthogonal to r prime at t naught. But we also have that del g is orthogonal to r prime at t naught. Thus, the gradient of f at x naught comma y naught is parallel to the gradient of g at x naught comma y naught. Oh, but by definition, what is it? What does it mean for two vectors to be parallel? Well, that means one's a scalar multiple of the other. Therefore, by definition, the gradient of g of x naught comma y naught is a scalar multiple of the gradient of f at x naught comma y naught. And since it's just some scalar, we may as well call it lambda, because why not? So the gradient of f at x naught comma y naught is equal to some scalar times the gradient of g at x naught comma y naught. And that concludes our proof. That's what we wanted to show, that the gradient of f, the objective function, is equal to some scalar multiple, lambda, times the gradient of the constraint function. And that makes us happy. So now let's take a look at some examples of using this to find some extrema of some functions, given certain constraints. Here, we're going to use this theorem, but let's go ahead and give an algorithm as to how this should be used. Because here, this is a statement of fact. But exactly how do you use this statement? So here, this is called the method of Lagrange multipliers. Basically, using this theorem in a more practical way. All right, so let f and g satisfy the conditions of the theorem above. Well, that one had a name, right? It was Lagrange's theorem. Okay. With f having an extrema subject to some level curve of g of x comma y equals to c. Then there are two steps. You're going to solve the system of equations. F sub x at x comma y equals lambda g sub x at x comma y. F sub y at x comma y equals lambda g sub y at x comma y, and g sub x comma y equals to c, the constraint. Here, it doesn't matter if we ever find what lambda is. Lambda is just some scalar multiple. It doesn't really matter what it is. Depending on the problem, you may find what it is or not. We don't care. What we care about are the values of x and y. So just keep that in mind. Lambda is sort of a stopgap measure. It's there to make the problem work. But if you find what lambda is, it doesn't really matter. So don't kill yourself trying to do that. It's a tool used to help us find the values of x and y. Okay? So the first thing you're going to do is you're going to solve the system. And then two, you're going to evaluate each solution from step one. So take whatever solutions you have, your x and your y. You're going to go and evaluate. The solutions from step number one. The greatest among these is the maximum. If there's only one, well, then that must be it, right? But if there are several, then the greatest among them is the maximum. The least among them is the minimum. And that's it. We can proceed. We can then proceed to use this method here to find the extrema of some functions. Here, this is the hard part. This is really just plugging in some numbers. And even this isn't terribly difficult, especially compared to some problems we've seen without using Lagrange multipliers. So let's consider some examples now. Let's go ahead and find the maximum. of the function f of x comma y equals 4xy. Here we're going to assume that x and y are both positive, subject to the constraint x squared over 3 squared plus y squared over 4 squared equals to 1. That's an ellipse. So you're trying to maximize this while making sure that whatever point you use to maximize it stays somewhere on this ellipse. All right, so here we go. First of all, let's let g of x comma y equal to x squared over 3 squared plus y squared over 4 squared. Okay. After all, in our theorem, we state that the constraint should be g of x comma y equals to a constant. That's exactly what this is. So this must be g of x comma y. Okay. Now let's find the gradient of f, where f is the function that we're trying to maximize. It's our objective. All right, well, that's not too bad. The derivative of this with respect to x, that's 4y, comma, the derivative of this with respect to y, that's going to be 4x. Okay, now let's find lambda times the gradient of g. All right, well, that's going to be lambda times, let's see, the gradient of g. The derivative of this with respect to x, that would be 2x over 9. And then with respect to y, that would be 2y over 16. And since you're multiplying that by lambda, you can write that as 2 lambda x over 9. Remember, lambda is a constant. We don't know what it is, but whatever it is, it's a constant. Comma 2 lambda y over 16. Right? So now, using the method of Lagrange multipliers, we're now going to take f sub x and have that equal to lambda g sub x. F sub y equals lambda g sub y. All right, so there's f sub x, and there's lambda g sub x. There's f sub y, and there's lambda g sub y. So we're going to set those equal to each other. We want to now solve the system of equations where 4y is equal to 2 lambda x over 9. We want 4x to equal 2 lambda y over 16. And I have to be careful that lambda looked like an x there for a second. And, well, a little bit bigger. And finally, we want our third one to be our original constraint. G of x comma y equals our constant. So that was the original constraint given in the problem. That'll be, what, x squared over 9 plus y squared over 16 equals to 1. So now we're going to solve for x and y. Notice we have 3 equations. We only need 2 variables solved for. If we solve for lambda, great, but all we really need are x and y. Since we have 3 equations to solve for 2 variables, this is eminently doable. Here, the pattern for solving something using lambda, the Lagrange multiplier, is usually pretty much the same. We're going to take one of our equations. I'm going to go and just work with the top one, and I'm going to solve for lambda. So here, if I solve for lambda, that's equal to, I'm going to go ahead and multiply both sides by 9 over 2x. All right? That gets rid of the 2x over 9. So if I multiply this side by 9 over 2x, I get 18y over x. Right? Yeah. Okay. So I went ahead and multiply here by 9 over 2x, and over here 9 over 2x. That makes all of this stuff go away, leaves me just my lambda, and that gives me 18y over x. Okay? So now take that and just plug that into your next equation right here. So that's going to be 4x equals, here 2 over 16, that's just 1 over 8. So let me just write that as an 8 right there. That's going to be lambda times y over 8. Oh, but I know lambda is, well, this stuff right here. So that's going to be 18y over x, that's my lambda, times y, over 8. All right, so it's going to give me 18y squared over 8x, which I can reduce to 9y squared over 4x. Wait, is that right? Yeah, that's right. So here that's going to give me, well, let me just do it in 2 stages here. 4x equals, that's going to be 18y squared over my 8x, like that. But now I can go ahead and multiply 8x over to this side, and let me divide the 4 over this way. So let me just say I'm going to multiply by x on both sides, and I'm going to divide by 4 on both sides. So that'll give me x squared equals, let's see, 18 over 8, that's 9 over 4 times another 4. So that'll be 9y squared over 16. Here, these divided away. So here that gives me just, these go away, it gives me x squared. Here, the number's reduced to 9 over 16, y squared. The x's have divided out. But now, I have x squared equals to this stuff, so now plug that into the remaining equation, and that'll help you solve for y. So now this gets plugged in over here. Notice the pattern. Solve for lambda, plug that in. Solve for one of the variables, plug that in. Now solve for your remaining variable. Here that's going to give us x squared is equal to 9y squared over 16, but that's getting divided by 9. Okay, so then that just gets rid of that 9. And I just get that x squared over 9 is equal to y squared over 16. So here this is going to give me y squared over 16. All right, that is that. Get divided by 9, makes that 9 go away. Y squared over 16 plus another y squared over 16 is equal to 1. Here that's going to give me y squared over 8 is equal to 1, which means y squared is equal to 8. I can take the square root of both sides, and here I should have plus or minus, but again at the beginning we had x and y are both positive. So here this would give me y is equal to the positive root of 8, which we can write as y is equal to the positive root, that's 2 root 2. And there we go. So we found our value of y. We can find our value of x by simply going back in and plugging that in. We have a constraint. That's probably the easiest one to use. We know that whatever values we have, this x and this y, when you add these together, has to equal to 1. So that's probably the simplest place to plug that back into. So now take this and plug into your constraint. Solve for lambda, plug that in. Solve for one variable, plug that in. Solve your remaining variable to get a constant. Now plug that constant into your constraint to find your other constant. That's going to give me x squared over 9 plus y squared over, so I'm taking my constraint, x squared over 9 plus y squared over 16. X squared over 9 plus, that's my y, squared over 16 equals to 1. If you square 2 root 2, that's the same as squaring the square root of 8. That's just the number 8. And if I take 8 divided by 16, that'll give me 1/2. So x squared over 9 plus 1/2 equals to 1. Subtract your 1/2 over, so that'll give you x squared over 9 equals to positive 1/2. Multiply both sides by 9, gives me x squared is equal to 9/2, and then take a square root. Since again I want x and y to both be positive, here I don't need to worry about a positive or negative root, it's just the positive root. So here this will give us the square root of 9 over 2, which I think I'll rationalize that. That's equal to 3 over root 2, and then I can rationalize by multiplying top and bottom by root 2. So this gives us x is equal to 3 root 2 on top over the square root of 4, or in other words just the number 2 on the bottom. There we go. So this gives us that 3 root 2 over 2, comma 2 root 2 our x and our y, that gives us an extrema. Now, we know this cannot be the minimum. You say, well, why not? Because over here, one solution to this would be, okay, I could set y equal to 0 and x would equal to 3. Oh, but if y is equal to 0, then my function would be 0, which is the minimum. You can't have an absolute value. You can't have something whose absolute value is less than 0. That's just, especially if here, both these are greater than 0. Here, these cannot get any smaller than 0. So that can't be the maximum. Okay, so 0 has to be the minimum. Okay, well, that's not 0, so that can't be the minimum. So that's got to be the maximum. So since there's only one, we don't really have to test anything. It can't be the minimum, since the minimum would be 0, so it's got to be the maximum. So now let's find what that maximum is. We're looking for the maximum of f of x comma y. So the maximum value of f of x comma y is at f of 3 root 2 over 2 comma 2 root 2, which is equal to 4 times the x times the y. So 4 times 3 root 2 over 2 times 2 root 2. Here that would give us, let's see, root 2 times root 2 is just the number 2. But then the number 2 would divide that number 2. So you're left with 4 times 3 is 12, times 2 is 24. So there's our answer. The maximum value of f of x comma y is 24. And you can find that whenever x is equal to 3 root 2 over 2 and y is equal to 2 root 2. Might wish to try this. Go ahead and give this a try. Go ahead and maximize the function. Go ahead and maximize f of x comma y is equal to x squared minus y squared with the constraint that 2y minus x squared equals to 0. And here we're going to go ahead and keep our values x and y positive. So just like before, there are no negative results at the end. Everything should be positive. Go ahead and give this a try. Pause the video, give yourself the time you need, and once you're done, go ahead and unpause and we'll go through it together. All right, so let's take a look. First of all, let's find the gradient of f. Okay, well that's going to be partial with respect to x is just 2x. The partial with respect to y, that's negative 2y. Let's go ahead and find lambda times the gradient of g. Okay, well, that's g. It's equal to a constant. Okay, so the gradient, the derivative with respect to x is negative 2x. Oh, but that's times lambda. Okay, so that'll be negative 2 lambda x, comma. The partial with respect to y is just the number 2. Oh, but then you have another lambda there, right? So it's going to be 2 lambda. Right? The gradient is negative 2x comma 2, but everything's being multiplied by a lambda. So now we want to solve the following system of equations. We want the partial of f with respect to x to equal to lambda times the partial of g with respect to x. We want f sub y to equal to lambda g sub y. And then we want our constraint to be the third equation of our system, that equal to 0. All right, so now we can solve. Here, this one's just a constant, right? Here we find that lambda is equal to -1. So as I mentioned before, you don't really need to find lambda. In the previous problem we didn't, but if it ever comes up, it doesn't change things either way. You don't need to find lambda, but occasionally in the process of solving, you'll find it. So here lambda must equal to -1. So right here we can plug that in right here. That is now -2y is equal to 2 times lambda. 2 times -1 is -2. And that suggests that y must equal to 1. Oh, so now I know what y is. So now let's plug that into that final equation. That gives us 2 times 1 minus x squared is equal to 0. That means 2 is equal to x squared, which means x must be the plus or minus root of 2. Oh, but no minus, all plus. That's going to be root 2. Okay, so we found our value of x. We can now find our value of y. Oh, actually, no, I take it back. We already found our value of y. So there we go. Here, this cannot be the minimum, because here, one solution to this equation would be 0, 0. And if you plugged in 0, 0 up here, you would get 0, which is the smallest possible value anything can be, right? And if you keep everything positive. So that means that obviously this is not going to be a minimum. So this must be a maximum. So let's go ahead and plug things in and see what we get. So f of root 2 comma 1. Let's see here, that's equal to 2 times y minus the root of, oh, sorry, I'm plugging it into the wrong function, aren't I? I'm supposed to be doing this one up here. So that should be x squared. So that's going to be root 2 squared minus, here we're going to plug in 1 squared. Root 2 squared is just the number 2, minus 1 squared is the number 1, and we get equal to 1. So obviously that's not the minimum, because over here we found that 0 is a potential answer, so that can't be the minimum, but we know it's an extrema, so it must be the maximum. All right? So that means that the maximum value of f of x comma y is 1 at the point, what did we say, root 2 comma 1. And there's a result, which is significantly simpler than some of our other methods of finding extrema. Something to note, the method of the Lagrange multiplier is extremely flexible. You can increase the number of variables without really changing anything about the nature of these problems. Here, let's go ahead and maximize not a function of 2 variables, but a function of 3 variables. Let's go ahead and maximize f of x comma y comma z, which is equal to x plus y plus z. So we're going to maximize the sum of those 3 numbers, subject to the constraint x squared plus y squared plus z squared equals to 1. So you want to find the point on the unit sphere such that if you add the 3 components together, the 3 coordinates together, you get the biggest possible number. All right? And here we're going to go ahead and limit things to the first quadrant. We want to limit things so that x, y, and z are all greater than 0. All right, well, this will work pretty much the same way. We're going to go ahead and take the system of equations. Normally we'd have f sub x is equal to lambda g sub x, and we'd have f sub y equals lambda g sub y. But now you have a third variable. Okay, so you'll have a third equation. F sub z equals lambda g sub z. And then the last one is still going to be your constraint. It's going to be g is equal to your constant. All right, so let's see what all those are. The derivative with respect to x of our function, well, that's just the number 1, equals. The derivative with respect to x of g, well, it's going to be 2x. All these would be 0. So 2x times your lambda. The derivative of f with respect to y, that's also 1. The derivative of g with respect to y, that's 2y times your lambda. So 2 lambda y. The derivative of f with respect to z is also 1. Here. The derivative of g with respect to z, that's going to be 2z times your lambda, 2 lambda z. And then we have our constraint, which is x squared plus y squared plus z squared equals to 1. So in spite of the fact that we have now a function of 3 variables rather than 2, all that you're doing is you're adding one more line to your system of equations. If you had a function of 4 variables, you just add another line. So now these can be solved. Here, let me take the first one and solve for lambda. Lambda is equal to 1 over 2x. Okay. Let me go ahead and plug that into the remaining equation here. So that one goes in there. And I have, let me do this over to the side. That would be 2 times that thing times y. 2 times 1 over 2x times y. The 2's divide away, and we're left with a y times an x. Okay. So that'll be 1 equals, there should be a y times a 1 over x. So I guess I'll just write y over x. Okay. Here, if y over x is equal to 1, that's the same thing as saying x and y are equal to each other, right? You multiply the x over this way. Okay. Now, right here, we can take that lambda that we found before and plug that in. And it's going to be pretty much the same thing. I'm going to have 2 times that thing times z. So 2 times 1 over 2x times z. The 2's will divide away, and we're left with z times 1 over x. In other words, z over x. So here, if I plug that in here, I get z over x is equal to 1. Which means I can multiply the z over, and I get x is equal to z. So now I have these two statements, x is equal to y and z is equal to y. So taking both of those and plugging them into my final equation, into my constraint, gives me x squared plus, well, x and y are interchangeable, so I'll call that another x squared. And here x and z are also interchangeable, so I'll call that another x squared. So this will give me 3x squared equals to 1. Or in other words, it will give me x squared is equal to 1/3, which is the same as saying x is equal to the square root of 1, which is 1, over the square root of 3. Right? Taking the square root of both sides. Here I should have a plus or minus root, but of course here I know that y, x, and z are all positive. So here I don't need the negative root. And let me go ahead and rationalize this. So this gives me that I find x equals root 3 over 3. But then we also found that x and y are interchangeable. Likewise, x and z are interchangeable. So that means y must also equal to root 3 over 3, and z must also equal to root 3 over 3. So, in the end, I'm trying to maximize this function. The maximum value of f of x comma y comma z is going to be root 3 over 3 plus root 3 over 3 plus root 3 over 3. You're adding the x, the y, and the z, which is 3 root 3 over 3. Now the 3's would divide away, and you're just left with root 3. So the maximum value of this function is the square root of 3 at the point root 3 over 3, comma root 3 over 3, comma root 3 over 3. Which, in spite of the fact that I now have a function of 3 variables, whereas our last few examples were functions of 2 variables, that doesn't seem significantly more involved. Now you might say that's because the first ones are so involved, but, well, for whatever the reason, this doesn't seem any more complicated than what we've already seen. Okay. Finally, for this section, we have one last example. The method of Lagrange multipliers is so flexible that we can increase the number of variables in our objective function. We can also increase the number of constraints. So here, let's maximize the function f of x, y, z equals x squared plus y squared plus z squared, subject to the following two constraints. Subject to x plus 2z equals to 6, and x plus y equals to 12. All right, well, here we go. We're going to want, all right, that's a function of three variables. So we're going to find f sub x equals lambda g sub x. F sub y equals lambda g sub y. F sub z equals lambda g sub z. And then normally we would have our constraint as the last equation of our system, but since there's two constraints, well then we have two more equations to our system. X plus 2z is equal to 6, and x plus y is equal to 12. So here, that's going to be, all right, the partial with respect to x, that's 2x. Here, the partial of, oh, let's see here. Oh, actually, I've made a mistake. My notation is wrong. Here, I have two different functions. So this one would be something like maybe g1 of x comma y is equal to a constant, and this one would be g2 of x comma y would equal to some other constant. So here, when we have g, we have to be more specific. We have to say which one. So my apologies. In fact, let me start this one over. So we're going to maximize f of x comma y comma z equals x squared plus y squared plus z squared, subject to x plus 2z equals 6 and x plus y equals to 12. So here, as I mentioned, I'm going to call one of these, I'll call this one g1 of x comma y, and that's equal to a constant. And then g2 of x comma y, that's equal to some potentially other constant. All right, so my notation will look something like this. I'm still going to want my f sub x to equal to a constant times the variable with the derivative with respect to x of my constraint. But since there's more than one constraint, I'm going to need more than one constant. So here I'm going to say, okay, that's going to be g, let's see, g sub 1x, like that, meaning the partial with respect to x of g sub 1. And here that's going to be times lambda. But now I have to do it for this one too. So here, those probably are not going to have the same constant. So here I'm going to use something besides lambda. I'll use another Greek letter. Let's go with mu. You don't have to worry about the names of these, but if you're wondering what I'm saying, this is, again, this is lambda, and this is mu. I guess that would be the, romanticization. Oh, actually, now that I think about it, I think it's usually spelled mu, but it's pronounced like mu. Like the sound a cat makes, I guess. So that's going to be lambda g sub 1x plus mu, and again, mu is just some other constant. It's just another Lagrange multiplier of g2 sub x. And then I'll have f sub y equals lambda g1 sub x plus mu g, sorry, that should be g1 sub y, and that'll be g2 sub y. Then I'll have f sub z is equal to lambda g1 sub z plus mu g2 sub z. Now, the only reason I have some space there, so it's starting to get a little cluttered. And then I'd have my constraints, which is going to be what, I guess just g1 equals to my first constant, and then g2 equals to my second constant. So if you have two constraints, you're going to have to take the partials with respect to both, and each one gets its own constant, and you're adding them together. If you had a third constraint, well, then you would say plus, and you'd find some other Greek letter, lambda, mu, and nambla or something, times g3 sub x. Whatever letter Greek letter you want to use next. Oh, maybe not nabla, because nabla looks like the gradient operation. Omega, whatever letter you wanted to use. So here, for this particular example, that's going to be, all right, the partial with respect to x, that's going to be 2x plus, not plus, equals lambda times the gradient of this first one with respect to x, which is just the number 1. Okay, so lambda times 1 is just lambda, plus mu times the gradient of the second one with respect to x. Well, that's also just the number 1. So mu times 1, I'll just leave it as mu. So now the derivative of f with respect to y, that's 2y, equals mu times g1 sub y. The derivative of this one with respect to y is actually 0. Okay, so maybe I should just not even write that one. Plus mu times the derivative of the second one with respect to y, which is just the number 1. So I'll just write mu like that. And then we're going to take the partial of f with respect to z. That'll be 2z equals lambda times the derivative of the first function with respect to z. So that'll be the number 2. So 2 lambda plus mu times the derivative of the second one with respect to z, which appears to be 0. So here I think I'll just leave that one off. Okay. And then here, that's just my other two constraints, x plus 2z equals to 6, and x plus y equals to 12. And since things are looking a little messy, I think I'll just rewrite things down here. So that'll be 2x equals lambda plus mu, 2y equals to just mu, 2z equals to 2 lambda, and then my constraints, x plus 2z equals to 6, and x plus y equals to 12. All right, so now I can proceed to solve. Notice I don't really care what lambda or mu are. Those are placeholders. I really only care what x, y, and z are equal to. All right. Looking at these two, just the top two, note that mu is equal to 2x minus lambda, but mu is also equal to 2y, which means that 2x minus lambda is equal to 2y. You can subtract your 2y this way and add your lambda over the other way, and that'll give us lambda is equal to 2x minus 2y. Okay, so this can now replace down here. This lambda, plugging it into this equation right here, gives us 2z is equal to 2 times lambda is equal to 2 times 2x minus 2y. Okay. Or more simply, here we can just divide the 2's out, and that gives us z is equal to 2x minus 2y. So now I have, let's rewrite some stuff here. I now have a smaller system of equations. I have z is equal to 2x minus 2y. I have x plus 2z equals 6. And I have x plus y equals 12. Here, I could combine these two to give me, well, let's see, that's going to be double this stuff right here. So that'll be 4x minus 4y. But then I add another x, so that'll be 5x minus 4y. 5x minus 4y equals to 6. And again, all I've done is I've taken that z and I've plugged it in right there. Leaving the bottom equation alone, I am now left with a nice simple system of two variables. Okay. Let's see, here let me multiply the bottom line by 4. And that'll give me 5x minus 4y equals 6. That'll give me 4x plus 4y equals 48. And so by adding these lines together, we get, that goes away, we get 9x equals 54. And if I divide both sides by 9, I get x equals 6. All right, so there we go. We find our value of x equals to 6. Now we can backtrack a little and figure out what our remaining variables are. Going back to our initial constraints, notice that x plus 2z is equal to 6. Okay, so x plus 2z is equal to 6. I'm taking the initial constraint here. X plus 2z is equal to 6. X plus 2z is equal to 6. And I'm plugging in the x that I now know. Oh, so I can subtract 6 from both sides. This gives us 2z equals 0. And then divide both sides by 2, which still gives us 0. So it turns out x is 6, but z needs to be 0. And finally, y, well, it looks like x plus y is equal to 12. So x plus y equals to 12. But we just found x is equal to 6. So subtracting 6 from both sides, we get y is equal to 6 as well. And so that will give us the maximum value of our z, of our f. So now that we have these values, we can turn to answer our question where we're asked to minimize. Oh, my apologies. That should be minimize. Minimize. You can't maximize this one because here you can make this, for example, if I want to make x a billion, well then I can just make this negative a billion minus 12, right? So that would give me 12 anyway. But since here you're squaring these, if I can make this a huge positive number and this a slightly less huge negative number, well then they're both going to be positive when you square them, so this will grow without bounds. I want to make this 1,012,000,012. I can make this negative 1,000,000,000,000, and yeah, that'll work. So right here I can also find a z that'll make that work. And when I square them, some will be positive, some will be negative, but all of them will become positive when I square them. So this will grow without bounds. So yeah, that doesn't have a maximum. Here the question was we're trying to minimize this. So now we can actually answer the question. We're minimizing this function. We now know the values of x, y, and z that have that happen. So we can go ahead and plug that in. F of 6, 6, 0, that's equal to 6 squared plus 6 squared plus 0 squared, x squared plus y squared plus z squared, 6 squared plus 6 squared plus 0 squared. That'll give us 36 plus 36 plus 0, which is 72. So the maximum value, oh sorry, I said it again, the minimum value. There is no maximum value to this. The minimum value of f of x comma y comma z is 72, which occurs I guess I can say at the point 6, 6, 0. And that makes us happy. So that brings us to the end of this section and the end of this topic. If anybody has any questions, comments, or problems on this, please make a note of those, reach out, and I hope everyone has a nice day.